All right, so the last thing I want to talk to you about is some of the things we have to do with the raw data to get it to be useful to us, okay? So the first thing, and you're going to see that this first statement is not necessarily correct, but basically, when we take a refractive index, the refractive index changes if the temperature changes, because the density changes, and density affects the refractive index. And so they decided that there should be a kind of quote unquote standard temperature for refractive indexes, and they decided that that was exactly 20 degrees Celsius. And actually, I should have put a dot there or a 0, but it's exactly, 20 degrees Celsius is the standard temperature. So if you go look up a refractive index and it doesn't have any temperature associated with it, you should assume that it was 20 degrees. Now, the problem with that is that if we go look up refractive indexes in a reference book, very often the people in the laboratory, they couldn't get it at exactly 20 degrees. And rather than doing anything, they reported their exact data and they give a temperature. So what that would look like, let's say we recorded ours at 22.3, we would write a superscript 22.3. So this is the temperature that it was recorded at. And so if you go look up in the textbooks or in the reference books, you very often might see that little superscript. Okay, what does that mean? Well, that means it was recorded at this temperature. So what we're going to need to do is convert that to 20 degrees. Now, the refractive index, I can show you right here. Okay, the refractive index, the symbol for the refractive index is this lowercase letter n. So this is the so in the same way that velocity is always a lowercase v and mass is always a lowercase m and so forth when physicists write their algebraic equations. So this n, that's the variable that's used to indicate refractive index. Now, this d is the wavelength of light. Because it turns out that light at different wavelengths bends a different amount. Okay? And so in order to get a repeatable thing, we have to always use the same wavelength. Now, what this is, this stands for the D line of sodium, and it's actually a wavelength of light that's used quite a bit. Okay? It's approximately, if I recall, it's approximately 520 nanometers, but don't take that as thing. I'd have to go look up exactly what it is. And what it represents, and I don't know if you've ever seen this. This is one of the things that I don't know that we do a great job in our general chemistry here, because our general chemistry is really old-fashioned, and they kind of skip spectroscopy, which is like super important modern stuff. But at any rate, so if you take light, you put it through a prism, it separates all the wavelengths. And what you can do is you can take light from different sources and look at what wavelengths are in there. If we take sodium and we heat it up to a very high temperature, the sodium itself will glow and give off light. If we then put a prism on it, we'll see that it's not giving off every wavelength. It's only giving off certain wavelengths, and I don't know exactly what they are, but you get these colored lines. Okay, that's totally inaccurate, but I could go find a thing. And so what this is supposed to be is it's supposed to be all black because there's no light there, and then these brightly colored lines, sorry, are there. And then what the physicists did was they just assigned each line a letter in order. And so the D line of sodium is the fourth line that's given off, and it corresponds to 520, which is not accurately shown here. And that's just how they can identify to everybody so that everybody knows which wavelength of light to use. At any rate, it's used for a lot of things. It's used for polarimetry. It's used for refractive index. Okay. And then this here, that's the temperature. So the refractive index is often in textbooks given as ND20. ND20. Okay. Well, what if we don't have it at 20? Well, we can adjust. Okay. So what we do is we take our experimental temperature value at the temperature experimental right here, and then we just adjust it by taking 22.3 minus 20, multiplying it times this, and then adding it to the refractive index. Okay, so we can change that to 20 degrees. We should always do that, and we should always report them as 20 degrees. That way, they can be usable by everybody. Okay. All right. The other thing I want to talk to you about is how we can use the refractive index to actually measure the composition of a mixture of two substances. So I kind of want to just really quickly walk you through this. There's some formulas at the bottom, and you can just skip to those if you want. But let me show you how they did these, because I think this is like a really useful, like how can you use algebra to set up what you need, okay? So here's how they did this. So assume we have two substances. So what we can do is we can make mixtures of the two substances, mixtures of certain amounts of moles, okay? Okay, so I put a little formula here. I have to apologize. So technically what we work with is what's called the mole fraction. And the mole fraction is for substance A, for example, it's the number of moles of A, okay, over the total number of moles, which would be moles of A plus moles of B, right? So it's like we have this many moles, this much is A, what fraction of the total is A? So this number is always between 0 and 1, okay? But we tend to like percentages. They tend to say a little more. So they multiply times 100 and they get a mole percent, which is basically the same thing as the mole fraction, just multiply times 100. And they use this letter X. Letter X is actually supposed to be the mole fraction, but the diagram that I was copying here used the percentage. So, okay, that's my mistake. I should probably make them real fractions. All right, so what we have here then is if I have only substance A, my mole fraction would be 100% A, because there'd be, moles of B would be 0. So I would just have moles of A over moles of A be 1 times 100. Okay. And if I start adding in substance B, then what happens is the percent of A goes down, but the percent of B goes up by the same amount that the percent of A went down, so that they always add up to 100. On this side, then I have 100% B, 0% A. And so again, we've talked about how these mole fraction plotted along the bottom, for a binary mixture of two substances, it's every possible composition. Okay. So what we want to look at is it's very possible that we might know the refractive index of substance A when it's 100% pure. And we might also know the refractive index of substance B when it's 100% pure. These are things we can look up, or if we can get a pure sample, we can just measure. All right. And so now what we want to know is, how does that refractive index change if we mix them together? So for example, if I have 50% A, 50% B, what is my refractive index of my mixture going to be? Okay. Well, it turns out that unlike Raoult's law kinds of things, like the boiling temperature and the melting point, everything where we saw these weird curves, this turns out to be a completely linear relationship. Okay. So what I mean by that is, if we look, this is the difference between these two. So for example, if this was 1.350 and this was 1.40, right? Then the distance here would be 1.40 minus 1.350. It would be 0.050, right? So whatever that distance is. And it turns out that what's going to happen is, if we're, for example, at 50%, we're going to have started at our lower number and moved up exactly 50% of the distance between them. Okay. So what does that mean? Well, what that means is, here's the distance between them. It's n of B minus n of A. This number right there, if we look, since we start at 0 here and we go up, that number there is 50%. This number here would be like 70% and so forth, right? Now, unfortunately, again, we did it as a percent. It really needs to be 0.5, 0.7 for this to work, right? It needs to be the mole fraction. But you can see that then what I'm saying is, here we're at 0.5 mole fraction of B. That's 0.5 multiplied times this number is going to be half that distance. Okay? So that's a really simple relationship. So then what we're going to do is, we're going to take that and we're going to put that all together. So what we have is, we have our starting point, that's right here, and then we add whatever our mole fraction is times the distance between them. So we get this number, this formula right there. Okay? And in theory, all we really have to do is plug in to this formula. So for example, this would be what we measured. This would be our experimental value. We would know this from the literature. We would know this from the literature. We would know that from the literature. It's the same as the first one. The only thing we wouldn't know would be the mole fraction of B. So we would just substitute in, solve for x of B, and then that would be our mole fraction. What we can do is, we can manipulate this algebraically, which I've gone ahead and done. You basically just subtract n of A and then divide by this, and you get this formula here. Okay. And then the one that I forgot to put on here is that. We get that because x of A plus x of B equals 1. And so if you solve for x of A, you get that. So what that means is, we can take this number and the things we look up, we can measure our mixture and tell exactly what percentage of moles we have in that mixture. Okay? That's awesome. That works great. There's one problem, and I'm just going to briefly tell you about this, and then it's going to come up in the lab, and I'm going to give you some data about it. All right? So this only works for ideal mixtures. Ideal mixtures are mixtures where the two substances don't have any strong attractive forces. So they can have London dispersion forces, and that's fine, because those are weak forces and they don't cause density changes, okay? But when you have a mixture of two substances that hydrogen bond, which is where we really often see this, what happens is the hydrogen bond creates an attractive force between the two particles, which causes the particles to pull together, which means that that whole solution sort of shrinks a little bit and it becomes more dense. And the change in the density is not just the change of mixing one with another, it's actually a change of that whole mixture shrinking, and the amount of shrinking or whatever depends on the composition of the mixture. So you have both this refractive index thing, but then you have this change in density, and it causes that line to not be linear. Okay. And in fact, with ethanol water, which is what we're going to be working, what it does is it actually goes up and then it comes back down a little bit at the end. So that messes up our math. And I was aware of the problem in general, but I didn't realize it specifically. So I set up the experiment and we started taking measurements, and we got percentages greater than 100% because the refractive index went too high. And so then I went and did some research, and I found a paper that has some numbers. It's quite old. I may have to redo that, but I'm going to try to get some data off of that so we can see if we can figure out more accurately where we are.